I'm going to review the topics from Module 6 in order to prepare you for the Module 6 test. So number 1, we're given f of x equals x squared minus 9 and g of x equals the square root of x plus 3. We want to find f of g of x and f of g of 3. So I'm going to first start with finding f of g of x. So with compositions, the second function always gets plugged in the first, which means I'm going to replace the x in x squared minus 9 with my equation g. So we're going to start off with the square root of x plus 3 squared minus 9. Now when we square root, they cancel, so I'm left with x plus 3 minus 9. And after combining like terms, we get x minus 6. So that's our equation f of g of x. Now we want to find f of g of 3. So now what I want to do is I want to take the number 3 and plug it in for x in my composition equation. So we're going to get 3 minus 6, which is then going to equal negative 3. In number 2, we want to find the inverse of the function h of x equals 3x minus 8. So my first step is going to rewrite my equation as y equals 3x minus 8. Then I want to switch x and y, so we get x equals 3y minus 8. And now I want to work on resolving for y. So my first step is going to be to add 8 to both sides, so we get x plus 8 equals 3y. Then we're going to divide both sides by 3. So my inverse function, h inverse of x, is going to equal x plus 8 all over 3. On number 3, I want to check to see if the functions f of x equals x squared minus 9 and g of x equals the square root of x plus 9 are inverse functions. So first I want to find my composition f of g of x, which is the square root of x plus 9 squared minus 9. So we're left with x plus 9 minus 9, which then simplifies to x. So our first composition simplifies to x. So now we want to check to see if our second composition, g of f of x, also simplifies to x. So g of f of x is going to equal the square root of x squared plus 9 x squared minus 9 plus 9. Combining like terms, we're left with the square root of x squared, which just becomes x. So because both of my compositions equal x, the answer is yes, they are inverses. On number 4, we want to find the domain, range, and vertical and horizontal asymptotes for our function f of x equals 3 to the x minus 7. So the nice thing is, on every exponential function, the domain is always the same, negative infinity to infinity, because there is no limit on a value that I can plug in for x. I can plug in any number for x into our exponential function. The range is dependent on the value that's being added or subtracted at the end. So because we have this minus 7, that tells me the smallest value in our range. So my range is everything from negative 7 to infinity. Next, we want to look at our vertical and horizontal asymptotes. So vertical asymptotes for every exponential function are always the same, none. Because vertical asymptotes are based on values that are excluded from the domain, and since there are no values excluded from the domain of exponential functions, it's always none. There is, however, always a horizontal asymptote. Ranges are always restricted on exponential functions, so Again, we look at that number that's being added or subtracted, and that's where our horizontal asymptote is. So in this case, it's going to be y equals -7. So domain and vertical asymptote tie directly to each other, and then the range and the horizontal asymptote tie together. So next we're going to take a look at solving some exponential and logarithmic equations. So number 5, we want to solve 4 to the x plus 1 equals 256. So this is an example from section 3 where we're going to rewrite the numbers with the same base. So we're going to leave the 4 to the x plus 1 alone, and then we want to rewrite 256 as 4 raised to a power. So we can rewrite 256 as 4 to the 4th, since 4 times 4 times 4 times 4 gives us 256. Now that the base numbers are the same, in order to solve for x, we're going to set the exponents equal. So we're going to do x plus 1 equals 4. And to solve for x, we're going to subtract 1 from both sides, so we get x equals 3. On number 6, we want to solve 8 to the x equals 7. And we can't actually rewrite 7 as 8 raised to a power, which means we're going to have to convert our exponential equation to logarithmic form and solve from there. So remember, exponential form is b to the x equals a, and logarithmic form is log base b of a equals x. So we can use these generalized forms to help us convert an exponential equation to logarithmic form. So I'm going to have my log. The base number is going to be the base of the exponential equation, which is 8. The number we're equal to is going to go inside their logarithm, which is 7. And then we're going to be equal to our exponent x. Now, in order to evaluate the logarithm, log base 8 of 7, we want to use our change of base formula. So that says, in order to evaluate log base b of a, we do the log of a divided by the log of b. So in this case, we want to take log 7 and divide by log 8. It's extremely important when you evaluate the logarithms, you make sure to close the parentheses for the logarithm in the numerator before you divide it by the logarithm in the denominator. So once we do log 7 divided by log 8, we're going to get x equals 0.94. Number 7, we want to solve the equation log base 4 of 2x minus 1 equals 2. So in order to solve a logarithmic equation, we convert it to exponential form. So we're going to use those same generalized equations that we used in number 6. So to go from logarithmic to exponential form, my base of my logarithm becomes the base of my next exponential equation, so 4. The number we're equal to becomes our exponent, so 2. And then we're equal to what's in the parentheses, 2x minus 1. Now we want to evaluate our exponent. So 4 squared is 16 equals 2x minus 1. And now we solve our equation. So we're going to add 1 to both sides, and we get 17 equals 2x. Then we divide both sides by 2, and we get x equals 17 over 2. On number 8, we have log base 2 of x plus log base 2 of 3 equals 3. Before I can convert my logarithm to exponential form, I first have to write it as a single log. So anytime we're adding two logarithms, we combine them as a single log by multiplying. So we're going to have log base 2, and then when we do x times 3, we end up with 3x, and then we're still equal to 3. So now I convert to exponential form, and we get 2 to the 3rd equals 3x. 2 cubed is 8, so we get 8 equals 3x. Then we're going to divide both sides by 3, and we get x equals 8/3. On number 9, we want to rewrite our logarithms as single logs. So we have 5 log x minus log 10 plus log 8. So the first step in combining logarithms is to take any numbers that appear in front and rewrite them as the exponents. So that means that 5 is going to become the exponent of the x. So we're going to get log x to the 5th minus log 10 plus log 8. Now we're going to work our way left to right combining logarithms. So first we want to take log x to the 5th minus log 10 and combine it to a single logarithm. Anytime we're subtracting two logarithms, they get combined as division. So we end up with log x to the 5th over 10 plus log 8. Anytime we're adding two logarithms, they get combined as multiplication. So we end up with log 8x to the 5th over 10. The 8 only multiplies with the x to the 5th because it's technically 8 over 1. Now I check to see if I can simplify what's in the parentheses. And 8/10 can simplify to give us log 4x to the 5th over 5. And that is our combined logarithm in simplest form. I'm actually going to skip number 10 because we're not going to see something like it on the test, and we actually didn't really cover natural logs. They have the exact same properties as regular logs, so we would have done the exact same thing. So the last page is our section 6, the word problems involving exponential growth and decay. So for 11 and 12, we're going to use the scenario, the number of quality math teachers is declining in America. The number of teachers declines at a rate of 8.7% per year from 189,000 quality math teachers in 1980. In number 11, we want to know how many quality math teachers will there be in 2020. So we're going to start off with y equals, and then we're going to want our initial amount. So that's our starting number of teachers, which is 189,000. So we're going to have 189,000. And then in parentheses, it's either going to be 1 plus or 1 minus our rate. And that's all based on whether or not we're increasing or decreasing. So the word declines tells me that we're decreasing. So we're going to have 1 minus, and then we need to write our percentage as a decimal, which is 0.087. And then our exponent is going to be the time. So in this case, we're talking about the amount of time that's passed from 1980 to 2020, which is 40 years. So now I can evaluate this in a calculator. And we're going to get 4,957.8. But since we're talking about people, we can't have a decimal amount of people, so we want to round it to the nearest whole number, which is going to give us 4,958 teachers. In number 12, we want to solve for how long until there are 100,000 quality math teachers in America. So this time we're going to solve for our exponent. So we know our final amount, 100,000, equals our initial amount, 189,000. We go ahead and do the simplification of 1 minus 0.087, which to give us 0.913, and then our exponent x. The first step is going to be to get our exponent by itself. So we're going to divide both sides by 189,000. Now 100,000 divided by 189,000 is not a nice decimal, so I'm going to leave it in its simplest form, 100 over 189 equals 0.913 to the x. Similar to number 6 on the previous page, I'm now going to solve this exponential equation by converting to logarithmic form. So we're going to have log base 0.913 of 100 over 189 equals x. So in order to evaluate this logarithm, we're going to use our change of base. So log 100 over 189 divided by log 0.913. Once I evaluate those logarithms, we're going to find that x equals 6.99 years. Time, you're always going to be able to leave your answer as a decimal since we can have partial years. But anything like number 11, when we're talking about people, you always have to have a whole number answer. So in 13 and 14, we're going to use our compound interest formula. So remember from the notes, the compound interest formula is A equals P, and then in parentheses, 1 plus R over N, and our exponent NT. So in 13, we want to know how much money would be in an account yielding 4% interest compounded quarterly if I deposited $400 in the account and left it there for 5 years. So we're trying to solve for a final amount. So we're going to have A equals, P represents our initial amount, which in this case is $400. Then in parentheses, we're going to do 1 plus, R is our interest rate as a decimal, which in this case 4% as a decimal is 0.04, divided by N, which is the number of times interest is compounded in a year. So to figure out what that number is going to be, you look for the word that comes after compounded. In this case, it's compounded quarterly. Quarterly happens 4 times a year. So that means we're going to have our denominator of 4. And then our exponent, n again, so 4, times t, which is the amount of time in years. So 4 times 5. Now we're going to evaluate this equation in a calculator. And we're going to end up with $488.08. Because we are talking about money, it's important that you only round 2 decimal places and you have dollars in your final answer. Do not try to break up the steps for evaluating the formula in the calculator. Type it exactly as it appears in that Desmos scientific calculator that I posted on Classroom, or in your own calculator if you have one, so that you get the most accurate answer. In our last question, we have that $12,000 is invested in a savings account yielding 8% interest compounded semi-annually. How long until the money is doubled? So we're solving for time here since it says how long. So our final amount is based on the fact that we're doubling our initial amount. So double our initial amount is going to give us $24,000 equals our initial amount, $12,000. And then in parentheses, 1 plus 8% as a decimal is 0.08 over n. So this time the word after compounded is semi-annually, which occurs twice a year. And then our exponent is going to be 2t, since we don't know the time that's happening. Our first step is going to be to divide by 12,000. So 24,000 divided by 12,000 is going to be 2 equals, I'm going to go ahead and figure out what 1 plus 0.08 all over 2 is, which is 1.04, and then our exponent is still 2t. Just like in number 12, the only way we can solve this exponential equation is by converting to logarithmic form. So we're going to have log base 1.04 of 2 equals 2t. Using our change of base, we're going to have log 2 divided by log 1.04 equals 2t. Dividing log 2 by log 1.04 gives us 17.67299 equals 2t. Then we're going to divide both sides by 2, and we get t equals 8.84 years. Please let me know if you have any questions over anything from Module 6, or if you would like to talk more about any of these problems before you take your Module 6 test.